A net is something, it's like if we cut it out of paper and folded it up along the lines. Yeah, it would fold into some kind of three-dimensional shape. Now, right here, it says on number 1, for example, can you create equal parallel plane sections? And yeah, if this one was folded up, as it turns out, we would have a cube. Something like this one right here. And the cube, does it have parallel plane sections? Well, yeah, for example, this right side is parallel with this left side right here. Or if you wanted to, the front is parallel with the back. Or if you want, the top is parallel with the bottom. So, yes, the answer is yes to this question. So this one may be a little confusing, but what shape would this net make? No. Well, if we folded this up, this would give us. So I'm gonna make the circles the red part, and then this rectangle right here will be in black. You'll see. All right. So I've got the circles like these, and then I'm just gonna connect it with the black rectangle right here. This is the three-dimensional shape, which is also called a cylinder, and we can see the red portions right here, the circles, are also parallel plane sections. So yes, we could create equal parallel plane sections. All right, let's take a moment and just think about what shape this would create if we folded this up along the dotted lines. It would create a triangular prism. So let's go ahead and draw that out. All right, so again, can you create equal parallel plane sections onto these? Yes, you can. The two triangles right here, this one and then the one in the back right here, those are parallel, which is kind of what makes it a prism anyway. So the answer to this one is yes. All right, let's take a look at this net and figure out what shape this would make. This shape, if we folded it, we could see that all of the triangles would come together to a point right in the middle of that square in the top. So let's go ahead and draw what this would look like. All right, and to really make this look three-dimensional, we'll just put a point up here, and then we connect that point with all the edges. Then we'll clean it up. There we go. So this one will create a pyramid, but the question on this is, can you create equal parallel plane sections? No. As it turns out on this one, there are no parallel parts to a pyramid, so the answer is no. So here is our net. What shape would this make for us? A little bit more than just a rectangle, right, because it's a three-dimensional shape. Rectangle's two-dimensional. Yes, this one's going to make a rectangular prism. So if we looked at this, I guess. All right, so this is a rectangular prism right here. And does this have any equal parallel plane sections? Yeah, sure it does. Just like the other rectangular prism we saw. We could say that the right side right here is parallel to the left part, or for example, the front is parallel to the back. So yeah, this has some parallel plane sections. Now this shape right here, if we folded this up, what shape would we get? This one, would it give us a cube? Yeah, sure. Right, very good. If we folded it these, it would give us a cube. And yes, this would make a cube. Just to clarify, I mean, if we really wanted to fold it, I could say that this is the bottom, which would be down right here, the bottom. And then this would be maybe the right side, which is this one. This right here is the top. This would be the left portion. And then you have the front, in the front, and the back, in the back. So, can you create equal parallel plane sections on this one? Yes. Yeah, so this one, what shape is this going to give us when we're all finished folding it up?
No, pyramid.
Alright, it is a pyramid, but what type of pyramid?
Hexagonal pyramid.
Hexagonal pyramid. So the reason why it is a hexagonal is because this shape here in the base is a hexagon. Now you guys need to notice that as soon as you see a bunch of triangles like this, automatically you should know you're going to have a pyramid, alright? Because pyramids have triangles all the way around, no matter what type of pyramid it is. Unless it's circular, then it's just a cone. But in this case, if we were to draw it out, alright, so I have my hexagonal portion right here. And then at the top, I'm just going to put a point where all these will come together. Bam, something like this. There we go. That may look kind of pretty.
This one's no.
But yeah, this one's a pyramid. No pyramids, as far as we know, have any parallel plane sections. So this one is a no. So after folding up this one, what shape would we get?
Hexagon. Cube? Hexagon cube.
Alright, well, you're on the right track. It's pentagonal, because of the pentagon. So it's a pentagonal what?
Cube?
Yeah, this one's going to be a prism. Because, it doesn't have any triangles, so it's definitely not a pyramid. So it must be a prism, as far as we've gone over. Alright, just so we can see what this would look like after we folded it up. So that's a nice setup. Then we just connect the points like these. And we can clean that up a little bit. Alright, so something like this. And does this create equal parallel plane sections? Yeah, the pentagons are parallel to each other, which is, again, kind of the properties of a prism. So, yes. Alright, can we create equal parallel plane sections for this? What shape is this going to give us?
Triangular cube? Triangular prism?
Triangular prism, the two triangles, right account. Yeah, they're going to give us some triangles, right account. And then it's going to come back like these. And then we would connect these vertices like these. Alright, so yes, this would be a triangular prism. And can you create equal parallel plane sections? Yes, the two triangles are parallel. Alright, they told us that this net radicant will form a cube. I think we've seen it before. But if each square face of the cube has a side length of 4.2 centimeters, what would the surface area of that cube be? So what this means, let's take a closer look, is that each of the side lengths is 4.2, which is nice about a cube. You know, 4.2 there, 4.2, 4.2. I think that's pretty good in terms of the lengths that we have. Maybe this one, 4.2. Alright, so if I looked at the area of one of these squares, how would I find the area? Well, each length is 4.2, so I do 4.2 times 4.2 on my calculator. So I got 17.64. That's the area of one square. But how many of these squares does we have? 1, 2, 3, 4, 5, 6 of them. So I could easily just take this and multiply it by 6, which would give me the area of the whole shape. Which is, yeah. So that gives us 105.84 centimeters squared. Again, that's the area of the entire, I guess we'd call that a T shape. That would create the cube. So if each face of the cube has length 4.2 centimeters, what is the volume of the cube? So volume for a cube, same with any rectangular prism, is going to be length times width times height. And in this case, the length, width, and height are all the same. They're all 4.2, so I'm just going to replace those in there. And after plugging this into my calculator, I get, so I got 74.09, I rounded that, centimeters cubed. This is cubed because volume is three-dimensional, length, width, and height. So we do need to make sure we label that correctly. if you created a new cube with edge lengths that are 150% of the original cube of 4.2 centimeters, what would the new surface area and volume be? Alright, so let's figure out what the new lengths would be. So it's 4.2, and it's 150% of that, which as a decimal is 1.5. So if I multiply these, this tells me the length of the new cube, which is bigger. So that gives us lengths of 6.3. Now the area of one square would be 6.3 times 6.3, which is 36.69. So we're going to take that area, 36.69er, and we are going to multiply it by 6 because there's 6 of those side lengths in there. And that gives us 238.14 square centimeters would be the area of this new shape. So if you created a new cube with the edge that are 70% of the original, the 4.2, what would the new surface area and volume be? Oh, we needed the volume of the last one, didn't we?
Yeah.
So that one is 6.3 times 6.3 times 6.3, which is going to give us the volume of, so there we go, 250.05 centimeters cubed, which is pretty nice. All right, let's do the 70% one. So 70% of the original 4.2. So we got 4.2. Going to multiply this by 70%, or I could set up a percent proportion. And the new length is, so that gives me a new length of 2.94 centimeters. Each square is going to be then the area of each square, 2.94 times 2.94, because it's a square. Which is, I'm going to round this to the hundredths, 8.64 centimeters squared. Now we can't forget we have 6 of those. I'm going to multiply 6 times 8.64. That will tell me the area of the whole thing. So the area of the whole thing, 51.84 centimeters squared. Now let's go ahead and find the volume. So we're going to take that 2.94 again, and the length is the same, 2.94, and the width also 2.94. So we're just going to multiply these together, and I get 25.41 centimeters cubed for the volume. So would it require double the cardboard to make the box? The answer is no, but it's no because if you double the amount of cardboard, you don't have enough. So, for example, let's go ahead and draw a picture that may help. So if this is our box, and we wanted to figure out how much cardboard there is, that's what we should do actually. So I want the surface area of this thing. So I've got this side length on the right, which also matches the side length on the left, which is, let's go and label these dimensions. So the red rectangle has an area of 6 times 2, which is 12 square inches. But we have 2 of those sides, so that's 12 inches squared again. The front face, radical, matches this back face back there, which is a area of 6 times 4.5. 6 times 4.5 is 27 inches squared, and we have 2 of those. So last we need the bottom and the top, which have an area of 4.5 times 2, which is 9 square inches. But I have 1 to match it. So when I add all these together, that gives me a total surface area of, so that gives us 96 inches squared for the original. Now what we need to do is double these side lengths and then figure out the new area. Alright, so now it's a 12, 9, and 4, but it's a scaled version of this. So the new area of the red rectangles is going to be 12 times 4, which is 48. But we have 2 of those, so I got another 48. Then we can do the purple ones, which are 12 by 9er, which is 108, but we have 2 of those. And then next is the area of the green, which is a 4 by 9, which is 36. So when I add all those together, that will tell me how many square inches of the bigger box we need. So that's 384 square inches, which, as it turns out, should be 4 times the 96. Let's double check that. 96 times 4. The reason I'm multiplying it by 4 because I doubled, or I multiplied the scale factor by itself, and we doubled the lengths, so the area is multiplied by 4. 96 times 4 is 384. So that's why the answer here is no. So if all the dimensions are doubled, will it hold double the serial? Why or why not? The answer to this one is no, and this has to do with the scale factor as well. The regular scale factor is 2 because we doubled those measurements, but that caused the area scale factor to be 4. So what does that do to the volume scale factor? Well, we'd have to multiply that by 2 again, so that means we'd multiply it by 8. So as it turns out, I won't hold double the serial, it will hold 8 times the amount of serial as the original. So here's the problem with doubling the dimension, one dimension of this, is it doesn't double the amount of cardboard we need, because if I took the box, and let's say that I doubled the, I don't know, I'll double this length radical. So now we have a box, I don't know, something like this, radical. Well, this box isn't going to have double the amount of cardboard needed, because the face here on the right was the face that used to be right here. So we haven't doubled that amount from what we had originally. So the answer is no on this. It did not double the amount of cardboard needed. Then D, if one of the dimensions is doubled, will it hold double the amount of serial? Yes, it will. We can see that we just, in the diagram we just drew, that this box in black was duplicated with the box in red. So the answer to that one is a yes. A container of chocolate milk has the following dimensions: a square base with side lengths of 6 inches and a height of 9 inches. Alright, so I just want some space to draw this. So we got a square base and a height of 6 inches, side lengths of 6 inches and height of 9 inches. So this is our 9-inch rectangle radical. Alright, and that looks like it would make some square bases for us. So let's go ahead and label these. I got 6 inches, 6 inches, and then 9 inches as the height. So if all the dimensions are reduced by a scale factor of 1/3, will it require 1/3 the amount of materials to make the container? No, because if we cut those in thirds, and now it has side lengths of 2 inches, 2 inches, and 3 inches. So will it cut the amount of materials by 3? No. If you cut it down by thirds, then you would need 1/9 of the amount of the materials. And the reason that is because the scale factor is 1/3, so the area scale factor would be 1/3 times 1/3, which cuts it down into 1/9 of the amount of materials we need. So then if all the dimensions are reduced by a scale factor of 1/3, will it hold 1/3 of the amount of chocolate milk mix? No, because that's talking about volume. The volume scale factor is 1/3, the scale factor times the scale factor times the scale factor, which would be 1/27. That's a very small, much smaller amount than what was originally there, but yeah, it's 1/27. Then if the length of each side of the base is reduced by a scale factor of 1/3, how much surface area and volume will it have now? Let's go and figure that out. So it's just looking at the base now, which would give us, instead of a 6 by 6 by 9 square, it's going to end up being a 2 by 2 by 9 square. So the surface area, we have 6 parts to it. We got the 2 by 9er, which is 18. Well, we've got 2 of those. Then we've got the front, which would be also a 2 by 9, which is also 18. And then we got the bottom, which is a 2 by 2, which is 4. And we have 2 of those, one on the top, one on the bottom. Let's go and add those together. So the surface area is 80 inches squared. To find the volume, we're going to take 2 times 9er, and that would give us 36 inches cubed now, because it is three-dimensional. So what's the percent change of surface and area for volume C? Well, we got to go back and figure out what the original area was. Alright, so the original surface area would have been 288 inches cubed, and the volume simply would have been 6 times 6 times 9er, and that would give us a volume of 324 inches cubed. So to find the percent of change, we got to figure out how much it did change. So there's our original volume. Let's do surface area first now. So the surface area went from 288 to 80, which means it changed by 208. And we're going to divide that by the original amount, 288. So as a decimal, this is 0.72 repeating, which would be the same as about a 72% change. On the other hand, though, for the volume, it went from 324 inches cubed to 36 inches cubed, and the difference between those. So it changed by 288 cubic inches, but we're going to divide it by the original 324, which is 0.88 repeating. So we can say 88.9%. That would be the change for the volume. So what we're going to be doing is finding the surface area of this shape. So to do that, what we will do is we got to find the area of each of the shapes. I'm going to start with the box, particularly in the front right here, which also matches the back's portion of the box right here. And the area of that would be a 32 by 10 rectangle, which gives me 320 feet squared. But I've got 2 sets of those, so I've got another 320 right here. I'm going to need to add those together. Next, I'm going to focus on the left portion right here, which also matches the right side, the right face. And the area of that is a 32 by 10 again. So that's going to give us another 320 with another 320 on to match on the right. Next up, I'm going to focus on the bottom face, which is a 10 by 10 square. So that has an area of 100, which I need to add. Now that's the 5 faces of the box. What I need now is the area of one of these triangles, which actually is matched by all the other 4 triangles, which means I'm going to have 4 triangles to add to this area that I have already. So the base here is 10. We can see the height over there is 12. So the area of the triangle is going to be 12 times 10, but we're going to divide that by 2. That's 60 square feet, plus another 60 square feet, another 60, and another 60. That's all 4 of the triangles which when I add together, that will give me the total in square feet, the surface area of this shape. So that is 1,620 square footages. Alright, to start this shape, we're going to find the surface area of this shape, but it's going to be good for us to see how many faces there are first. So just from the box portion on the bottom, that's going to give us 5 faces. And then the triangular prism that's sitting on top of it appears that it will have 4 more faces to add on this. So we need 9 areas to add in order to find the area of this whole thing. But before we do that, it may be helpful just to clarify some values that aren't really showing on this. Because we have the triangles, which we're going to need the base value, which is 8 feet. But the height of that thing, since this one is 8 feet, it must have a height of 7 feet. Right here. So let's start this off by, let's work with the triangular prism first. So first off, I've got this, actually, oh yeah, we do. This, the area of that, it has a length of 8, and then this bottom part right here is 15, so it's an 8 by 15 rectangle, which gives us 120 square feet. Alright, as it turns out, the other rectangle on the other side there also has the same measurements, so 8 by 15. Now let's go ahead and do the triangles. There's 2 of them. So the area is going to be, it's an 8 by 7 triangle, but the area of the triangle is divided by 2. So that's 28, but we've got 2 of those triangles. So we've already identified the 4 areas from the triangular prism. The base, or the part that it's sitting on, isn't part of the surface, so it's not included in the surface area. Next up, I'm going to find the area of this rectangle, which matches the one in the back. And that area appears to be an 8 by 15 as well. So that would make that area 120 again. And then we got the one in the back to match. Next we got the side face, which also matches the right side face. And the area of that is an 8 by 8 square. So that's 64, but we have 2 of those. Next up is the bottom portion, which should be an 8. It's an 8 by 15 rectangle, but there's only one of them, so we got another 120 to add to that. We're going to add all these, and we are going to end up with feet squared because it's surface area. So let's go ahead and add. So we got 784 square foot. That would be the area. Yeah, I had to change this to a 4. I had written that down wrong, so 784 square feet is the surface area of this shape. Alright, last thing we need to do is be able to find the volume of any pyramid really. So the nice thing about any pyramid is that the volume for any pyramid, and this is something you guys are going to want in your notes, because when you see it on the test you're going to have to figure it out, is you're going to take the length times the width times the height, but that would be for a regular rectangular prism. For a pyramid, rectangular pyramid, we're just going to divide that by 3. Now on this one it didn't really give us the height. We'll just change this. And we'll say that the 5 inches is the height of this thing. So if I wanted to find the volume of this pyramid, I would do length 3 times the width 3 times the height is 5, and I would divide that by 3. That's going to give me a volume of 15 inches cubed.